structures. Konstantin, are you here?
Yes,
okay.
yes.
Okay, you can start, but you have only 15 minutes, okay? Okay, you can start.
My presentation named coercive force of magnetic sensitive nanostructures are cobalt nickel and gadolinium oxide. In nanoscale field structures consisting of contact layers of ion groups ferrum, cobalt, nickel, and rhodium oxide due to the exchange of the interaction between atoms with unfilled F and D electron shells. There is an ordering of the magnetic structures of ferromagnetic metals, thereby increasing many dependent from each properties, aerodynamic, magneto-optical, and others. It's a matter of possibilities of amplification of the properties in the mode of high frequency of remagnetization of nanostructures is revealed when considering coercive force as a characteristic equivalent of the magnetic field for demagnetization of matter. A significant increase in this force in the presence of exchange of the interactions would reveal the impossibility of using the achieved gain of magnetization and its dependent properties at high frequency. The aim of this work is to estimate the coercive force in iron cobalt nickel nanofilms before and after the application of the rhodium oxide layers. Before and after the occurrence of FD interaction, enhancing the magnetization of the metal layers. The value of force coercive was estimated from the hysteresis loop, which describes the curve of the field dependence of the resistance, the ferromagnetic metal of the magnetic fields when measuring the anomalous Hall effect. Since the anomalous Hall effect has a proportional dependence of this resistance of ferromagnetic metal on the magnetization. The hysteresis actuality describes the dependence of magnetization on these magnetic fields and can be used to determine a coercive force by the usual method. Comparing the coercive force volumes obtained in iron cobalt nickel films before and after application of a 100 nanometer thick gadolinium oxide films. It was shown that after application of the RAM layer, coercive force increased in nickel films from 0.08 to 0.1 kilostat. In ferrum, from 0.8 to 1 kilostat, and cobalt from 1 kilostat to 1.6 kilostat. The following volumes of coercive force allow us to draw the following conclusions. As in bulk samples of metals, ferrum, cobalt, nickel, the highest force is known as cobalt and losses in nickel. The application of the RAM of said layer leads to an increase in the magnetization and an increase in the coercive force of the metals iron, cobalt, nickel, to an increase in the magnetic fields required for the remagnetization of nanostructures, then increase in insignificant but should not lead to significantly complication during the operation. Nanostructures have recurrence. Thank you for attention.
Okay.
You
Okay. Thank you, Konstantin, for his talk. Maybe somebody have questions. You are welcome. No questions. Okay, so Konstantin, it is questions for me. What is the application of such nanostructures?
Application electron beam vacuum electron beam in vacuum for the temperature subtract 26 160 Celsius and the position rate of the layer 50 nanometer per minute in for pure nickel, ferrum, cobalt, and temperature with a layer gadolinium 2-3 25 Celsius degree, and working chamber pressure 20 decipascal.
Okay, thank you very much for the report and for answer. And currently, we are moving to the next presentation.
Mm-hmm.
And next presentation is improving the service life of firearms barrels by pulse plasma nitriding. And I would like to invite the presenter. It's Igor Smirnov from National Technical University of Ukraine, Igor Sikorsky Kyiv Polytechnic Institute. Igor, are you here? Are you with us?